So, good evening, everyone. Myself, Saurashish Chatterjee, and from today onwards, I'll be holding this problem-solving session for this Principle of Communication Systems 1 course every Saturday, 6 to 8. So, let us just wait for another 2-3 minutes. Others can join in the meantime, and then we can proceed. Okay, so I think we can begin. Just one more confirmation. You all can see what I can write also. Can one of you please confirm that whatever I'm writing in the red is visible to you or not? Okay, I'm assuming it's visible. So there are few things I would like to say that uh, anytime just feel free to interrupt me if you have any query. You can type queries in the chat box also, but since I'll be doing this writing in the PowerPoints, I may not be immediately able to see that. So just raise your hand or just interrupt me and ask me to look into chat box, and it's fine. And even after the session ends, if have any queries, I have given my email address below. You can contact me anytime. Hopefully I'll respond to within 2-3 days. So let us begin the session for the week 1. So as you all know that the content of week 1 is more about preparing you for what's coming. So the week 1 content is basically revolves around the basics of signal, and we are going to talk about this easy or smooth transition between time and frequency domain. So my plan is that I would like to discuss few questions throughout the session which are similar to assignments, like 9 to 10 questions, and instead of answering the question directly, because this is a like mostly objective type question, so you can answer within uh, like 15-20 seconds sometimes, but my idea to discuss the concepts behind it. So I'll just briefly recap what is being taught in the class, just to reiterate things again and again, so those things become easy for you, and you can answer any kind of similar questions. So let us begin with the first question of today's. So here we are going to ask the power of an energy signal. So it might sounds quite trivial to some of them, but not so trivial for others. So let us hinge on to 2 points here. So there are two key terms. One is power, and second is energy signal. Fine. So let us pick. Let's not even talk about energy signal initially. Let's talk about signal. So I'd prefer this class to be a bit interactive. So can one of you volunteer here to tell me what do you mean by signal? Like, let's say you have gone through week one content, I assume. So what is your just impression about do you mean by signal? Or basically, whenever you heard signal, what comes to your mind?
Dependent on two or more independent variable.
Okay, okay. So let us start with the simplest one. Let's make them dependent on one variable. Let's say we call it x of t. T is represented on a time domain. So function that is varying over time. Fine. So if I would like to draw that or interpret it visually, so let's say I have a signal of this kind. Mm, I have signal value here x of t, and x-axis is basically the variable axis, and we have a signal like this, a constant amplitude. Let's take amplitude to be 1, and it goes on till infinite. I know it's not really practical, but let's assume for sake of mathematics this is our signal. So when I talk about energy of signal, what do we exactly mean by that? Or let's talk about the math. What is the expression for energy of signal? So I have a signal xt. How can I write the energy of signal? Let's say I call it ex. So basically what I take absolute squared value of xt, this thing, and integrate over the entire range, minus infinity to infinity. This is the amount of energy content in a signal. So basically I take the absolute value square, so the amplitude square, and integrate it over the entire period from minus infinity to infinity, and that is what the energy of a signal is. Now whenever we talk about energy, inevitably another uh, term appears, that is power. So power of signal. So can you point out what do we mean by power of signal, like, or how we can interpret it mathematically? So for power of signal, the idea is something that we denote it by px. Just so it's px. So we are basically looking for the energy over a certain period here. So let's say the period we are talking about, it's t. So since we are looking about the uh, power over a single period, so the expression is something like this: minus t over 2 t over 2, rest of the content remains same. So it's as if like we are looking at the energy over an interval of size t. The main difference here is that we are not looking over the entire signal duration. Now we are interested in any uh, t duration. By the way, it need not to be minus t by 2 to t by 2 always. It can be any duration of t. Let's say it can be 0 to t, or maybe minus t by 4 to 5t by 4, something of that sort.
Sir, I think limit t tends to infinity, you are missing.
Yes. I'll come to that actually. Yeah, thanks for pointing out. But yeah, so that is what I mean by power. But this t duration I'm talking about, as you correctly mentioned, it has this particular value. It, it doesn't mean that px applies to all t. So this applies only when limit and t here tends to 0. So this is our energy expression and this is our power expression. So now we have talked about the energy and power of a signal. Now let's not get into the maths here. So if I ask you, I have draw a signal here. So xt basically takes value 1 for all t, and it, as you can assume, it go till infinity. So without even looking at math, can you point out what the energy this signal is going to contain? Just intuitively. I am not worried about the math, exact values and all that. A signal which has the amplitude like this 1, and basically the time tends to infinity, takes value 1. So what could be the energy? So even without the math we can see that the signal never dies out. So basically all the practical signal we know that goes on for a certain period of time, then the signal dies out. Here I am uh, making up some imaginary signal which takes a constant value 1 and goes to infinity is another way of saying it never dies out. So the energy should be infinity. That much we all can say without even looking at the math. So this is the concept of energy and power. Now when I say that energy signal, can one of you point out what exactly we mean by energy signal, or what is the difference between like the general class of signal and energy signal? It's like energy signal is a subset of this whole signal group.
Time signal is not time limited.
Uh, Sorry, can you repeat once? I'm not able to hear you.
Not time limited signal, it also periodic signal.
Okay, not let's write it down what you mentioned. Uh, Not time limited, you said, right?
Yes,
And you also mentioned about periodic.
periodic signal.
Okay, periodic signal. Fine. And by the way, when I say time limited, what can you clarify on this point once? Like elaborate on this. Like what exactly do you mean by not being time limited?
Because the periodic signal, it's the nature is the values is infinity time period.
Okay, okay, okay. From that point of view, okay, fine. So actually you are close, but I would like to point out here that energy signals are like I cannot really doesn't cover with these two properties here. Energy signal is something like signal having finite energy. So, but don't worry, we'll come to later to periodic signal also and the signals which are not time limited and how they fits in the argument. But energy signal is like simply signal which have basically finite energy. So that means this ex here takes some value c which is a finite value. Basically that doesn't go to infinity. So we know now energy signals are those signals which are having finite energy. Good enough. So now with this knowledge we have that this it's going to have a finite energy. Can we comment anything about the power of an energy signal? That is the question here. We have seen what signal is. We have seen the expressions of energy of signal and power of signal. We have looked into the definition of energy signal, and now I would like to get into the question here that with this knowledge can I infer something about the power of energy signal? Is it something signal dependent, or we can make a generic comment? For example, these options are given like 1 or 1 by 2 or 0 or infinity. What you think it can be? Or more likely I would like to know how you arrive at some conclusion about that. We have seen the energy expression, we have seen the power expression. We also know that energy signal has a finite energy c which is not infinity. Now based on that three argument, can I comment anything about the power of an energy signal? Or I cannot just comment because it's going to be that specific signal dependent? What do you think? So let me clarify this point here.
That is zero.
0, okay. But how can we arrive at this conclusion based on the knowledge we have as far? Fine, you are given a answer 0, nice. So but uh, how do I get that? Like if I want to proceed strictly via maths and not really intuition part.
No, the signal, its total energy E is a constant, and the finite number we
Okay,
plug into the P equal to limits t tends to infinity E by T.
okay,
So get the
correct.
smaller and smaller. So the finite number divided by the infinity is zero.
Okay, so let me just write down what you are saying. Let me introduce a slide here. So we have seen px as limit t tends to infinity 1 over t minus t over 2. Now this integration over minus t over 2 t by 2. So we can say this term is always lesser than 1 over t minus infinity to infinity xt square dt, and this entire thing is I'm evaluating at t at infinite. So this is my px and this is px 1 over t. You mentioned that this term now becomes my energy. So this is 1 over t over ex, and you pointed out this becomes ex over t. So ex we have already talked about, it's finite, but t here is infinite. So px is less than equal to a number which has t in the denominator, in t can be arbitrarily large. That's what infinity means. So essentially the px is 0. So your answer is correct only. The power of energy signal is 0. So the key idea, just a moment. Yep, just a moment. My system is getting hanged. Okay, it's fine now. So the key idea is to find the power of an energy signal. I need not know anything about the signal, what kind of in the sense what is the expression of xt. I don't need to look at the maths and all that. The moment I know it's energy signal, I can immediately infer the power of it's going to be 0. Nice. So now let us get into just the opposite of that, which is the energy of a power signal. So what is a power signal, by the way? Would you like to comment on that? You have already told me what energy signal is. Uh,
The signal which is having power, non-zero power, and which is finite.
okay. So you mentioned two nice points. It is having non-zero power, and you also mentioned this is also finite. So non-zero finite power. Fine. So according to your claim, the px now is 1 over t. These things take some value, let's say c, which is non-zero and finite. So what do you think the energy is going to be for this kind of power signal which is having a non-zero finite power? So we can make the similar argument, that is we have already written this expression here, and this is less than 1 over t minus infinity to infinity xt square dt. Remember, this is always going to be greater than 8 because here the interval is between minus t over 2 to t over 2. Here I am considering the entire duration from minus infinity to infinity. Now this thing here is what we already defined as the energy of the signal. So that is essentially saying that energy of the signal is greater greater than 2 px times t, and this is when evaluated t as infinity. So basically we have already discussed about the power. You mentioned it's non-zero and finite, so some finite number, some non-zero finite number times t, where t goes to infinity. So essentially your energy is infinite. So again, quite similar but at the same time opposite argument. We can see the moment we know a power signal, or like we basically classify a signal as power signal, we need not again look at its expression, like is that a sinusoid or is that exponential, whatever it is, it doesn't matter. The moment it's being classified as a power signal, it is bound to have energy which is infinite. So the fourth one is the answer. Now few moments ago one of you were talking about the periodic signal, which is kind of quite interesting. So let's pick one such signal here. Let me introduce a slide. So now briefly talk about the periodic signal. And take the easy example of, let's say, cos 2 pi f t. So by the way, when I say periodic signal, what do you mean by that? Like why it's periodic? I mean, as the name suggests, as if it repeats over a certain period of time. Is that what you are referring to?
The values of the signal repeat after some given time interval.
Okay. So the signal repeat itself over a certain interval, like that image we have drawn here. And to like specify a periodic signal, what are the parameters we need? Or maybe like one or maybe more than one parameters to specify periodic signal. Something comes to your mind, like what maybe the key parameter if I talk about a periodic signal?
The time period
Okay,
after the signal repeats.
so you are talking about the fundamental time period here. Let's call it t. So whenever I talk about a periodic signal, we have a fundamental time period of t, and that leads to a immediate conclusion of fundamental frequency. It's not, you quite well know, it's not something different, but kind of complementing each other. So what is the expression of f here?
1 by capital T.
Okay, 1 over t here. So basically this signal is repeating over time, and what is the basic time here? So over this time period, this function is unique, and once you go beyond that, it just keep on repeating. So let's say we assume this signal, this periodic signal only, and extend it both the minus infinity and infinity on time axis, what do you think it's going to be? It's a energy signal or power signal? For example, like I would like to see it from a slightly different perspective. If I call it energy signal, I have to show that its power is zero, and if I want to call it a power signal, I have to show that its energy is uh, infinite. No, like you can show also that power is finite. So both way it's fine. So what do you call such a periodic signal? Energy signal or power signal?
Yes, it is always the power signal
Okay, power signal here. And
because the pattern
okay,
never
yeah,
dies
sure,
out.
sure. Yeah, please go on.
That's meant the constant average flow of the energy or the total energy accumulated over the infinite time because it infinite. So the periodic signal is always the power signal.
Nice, nice, nice. So if I you explained it beautifully. So let us try to see like how can I find it as a powered signal, or maybe if I try to look at the power of it like compared to any random signal. Let's say there is some power signal which is you say aperiodic, that basically doesn't show a specific pattern or doesn't repeat itself over a certain period, and a periodic signal. So assume both are power signal. So whenever the signal becomes periodic, do we have any special advantage while computing the power of that? If I look at this expression here, is there something that separates uh, periodic signal from aperiodic signal? I mean, the power expression remains same for both of them, but whenever let's say by somehow I can see that signal is periodic, like does it make our job easier to find the power of that? And if it does, how so?
The limits are over one cycle of the signal, one cycle of.
Okay, so you are saying that this t here which is tends to infinity, and I have to take the integral over the whole t by 2 here. Now you say that we can replace the t here by the fundamental time period. Okay, correct, that is a nice conclusion, but I don't still see like how can I reach that stage from this expression. Can you guide me on that? I mean, I still have this expression of like from very fundamental. Let's say I don't know about the what the periodic signal is. I am still left with this power expression. So how can I reach the expression you are saying that is over a particular time period? What is the
The thing from integration minus t by 2 to t by 2, and after that is energy of the signal basically. So energy, we know that energy of the signal in one cycle is always zero. So we can put zero there.
okay? But if I make it zero, then how it becomes a power signal? I'm not quite getting it. Your inference is absolutely correct that for periodic signal we can compute its power by just observing it over a single period of time. That's absolutely true. But I'm just struggling to see how can I reach that conclusion from this. I mean, okay, let me just write it down here. Let's call it here t dash to separate from the fundamental time period. This is applicable for any power signal, and you are mentioning for periodic signal this px here reduces to 1 over t minus t over 2 to t over 2 xt square dt, where t is the fundamental time period. So this is the expression for generic uh, power expression, and this is the power expression that specifically apply to periodic signal. Absolutely correct. I'm just not able to see immediately how can I reach from this to this transition. Basically, how can I show that this is what happens for periodic signal from this. So you can see here we are talking about t dash tends to infinity, right? So t dash is pretty much a long time. I mean, let's not get into that infinite argument, but it's a pretty long period of time. So if it's long enough, you see that for periodic signal we can write t dash as some n times t, where n is the number of cycles basically, right? So if t dash tends to infinity, that essentially means t dash long enough, then we can, for periodic signal exclusively, we can write it n times the fundamental period, where n is the some number of cycles, some finite number. So can we infer anything from that? So let me just replace here px. I'm removing the limit as of now because it's not you can just keep it in mind. It's become n times t minus nt over 2 to nt over 2 xt square dt. So now any intuition we can apply here, so that from this we can reach to this. You earlier mentioned about period like energy in a period being zero. You are quite clear, like you are quite close but not exactly. So can you see how it's going to happen from this step to this step here? It's not exactly the energy being zero at every period. Your See here, I'm basically observing the uh, energy over n cycles, right? And you already mentioned that for periodic signal it basically repeats itself over a certain period of time, which is a tree here. So I can pick any cycle, the energy is going to be same because the pattern remains unique over a single time period. So this integral I can safely write it as n times the energy over a single cycle. And here remember what we have here, we have just 1 over nt. So these n's here both cancel out, and you are left with this expression which you have already mentioned, that is the power over a one single cycle. So this is one beauty of periodic signal. If it becomes aperiodic, we cannot do that. We are still stuck with this power computation, which might be computationally extensive because we have to observe over the entire duration to find what its power actually is. But the moment you declare it or somehow able to show it's a periodic signal, your job becomes much easier. You just observe the power over a single cycle, and that's pretty much it. You get its power. So with that, let us move to our next question here. So this has quite a few concept here. First is like about Fourier transform can be found for some continuous time signals and discrete times, and that another property periodic and aperiodic on all that. So before going into Fourier transform, let us talk about okay, we are left with the periodic signal, right? Let's say xt is periodic. Xt is periodic. So you have gone through the course. So what do you think if I claim the xt to be a periodic signal? Uh, what kind of frequency transform can be applied to it? Is it Fourier transform or Fourier series or something of that sort? Can one of you point out here? So basically we are talking about, as of now we are still was talking about a signal being a function of a single variable, that is our time. But now I am talking about Fourier transform and all that, and you can see there are different now. So these are, we are talking about frequency domain representation. So this is a good time to just talk about, like, whatever you see in the time domain, there is some equivalent representation of frequency domain. So your questions might be why we need that frequency domain. I mean, we can do whatever we want to do in the time domain itself. So it turns out, like when you talk about communication and signal processing, it all about analyzing and processing about signals, right? So sometimes what happen, the signals might be quite problematic in the sense, let's say they are overlapping on top of each other. So essentially the thing is the analysis become difficult in time domain. But what is observed, that if you have the frequency domain representation of the signal, the analysis suddenly becomes easy, and that applies on the opposite direction also. For example, if you have some signal frequency domain representation and which becomes quite challenging, I mean the analysis becomes quite challenging or its processing become extremely difficult, basically you are not able to get some insights or uh, stuff like that. So what happens, you can convert or bring it to the time domain representation of it, and suddenly things becomes much clear. So that's why this time frequency domain analysis is extremely crucial, because you can make a smooth transition between time and frequency. So in whatever domain you find your processing easier, because you can see that certain features or certain properties of signal are quite well visible in the frequency domain but not in time domain. And sometimes time domain analysis is much more clear and intuitive compared to their frequency domain. So that is why the when you talk about a signal, it has a frequency domain representation also and time domain. So we are talking about periodic signal, and periodic signal is going to have like is going to be of immense importance, and you will see in the next week of courses. So let's say, like, if I'm saying that xt is periodic, so what do you think its frequency domain representation is going to be? Frequency domain representation. So there are two things. One is already part of our question here, that is Fourier transform, and another thing is Fourier series. So can you tell me that for a periodic signal xt, which one applies? Like, are you going to do a Fourier transform or you are going for a Fourier series here? Any idea?
Fourier series.
Fourier series, okay. So can you tell me also one key difference between the Fourier transform and Fourier series? Both are frequency domain representation, but if you are asked about what is the like key difference between Fourier transform and Fourier series, what are you going to say?
Uh, if the signal is periodic, so it would have specific time period.
Okay,
So
fine.
the in Fourier series, we deal with fundamental frequency, that
Okay,
is fundamental time period. So we would prefer Fourier series in periodic signals.
nice. Okay, that's absolutely true. But I was like just hoping like, is there any like difference between Fourier series and Fourier transform in terms of being continuous or being discrete of this kind maybe?
Yes, the Fourier series is usually analyzed in terms of discrete.
Discrete
Uh,
frequencies. Okay, nice. Okay, so you are absolutely correct. So this xt here,
Fourier transform,
yes.
both the time and the frequency are continuous in Fourier transform.
Uh, can you please repeat once?
So the Fourier series, the time is continuous, frequency is discrete.
Okay,
But the Fourier transform, both time and the frequency are continuous.
okay, okay. Nice, nice. So let's, as of now, we talk about this periodic signal here. So this we can write as ck e to the power j 2 pi k f t, and your k basically runs from minus infinity to infinity. So, so if I try to see the spectra here in the frequency domain, as you correctly mentioned, this is a Fourier series is about more about discrete. So if I plan to draw my spectra here, so I'll only see non-zero elements at multiples of f here. By the way, f, as you mentioned, is fundamental period. So what I'm going to observe here, like this is c0 and this is, let's say, c1, this is c minus 1, similarly c minus 2, c2, like that. So this is f axis, so that is Fourier series is discrete. This is at f, this is at 2f, at 0, minus f, minus 2f. And one thing I am having trouble to understand, like xt is periodic with sorry, this is fundamental frequency here. So xt is periodic with fundamental time period t, and I get that fundamental frequency is 1 over t, that we denote as f. But what are these terms like? Do they have specific name? Because it is not that it only have content at fundamental frequency f only, it had contents in multiples of f, right? I mean, uh, 2f, 3f, so on, and ideally it extends to infinity. So what are they calls really? And this ck also, do they have some specific name? So xt is periodic with fundamental time period t, so it has a fundamental frequency f, that is 1 over t. Fine. But when I look at the frequency domain representation, it turns out it has non-zero elements at all integer multiples of f. So do they have any specific name, like and what is this coefficient ck is also called? These two are my questions. So basically these are harmonics. So even if my signal is periodic with period f, it is not going to be have a non-zero value at f. The moment
Sir, slide is not visible, sir.
okay, just a moment. Uh, is it visible now?
No, sir.
Okay.
Sir, now visible.
Okay, now it's visible, na? Thanks for pointing out.
Yes, sir, now visible.
Sure, sure. Yeah. So I was talking about even if my signal has fundamental frequency f, it doesn't mean the spectra is non-zero only at f. The non-zero component will keep appearing at every harmonics of the original frequency, and these ck's are called, as you know, these are Fourier coefficients. So this is xt, this is its Fourier series representation, and can you point out if I plan to find this ck here, like let's say the Fourier coefficient corresponding to kth harmonic, let's say k is equal to 3, and I am given the expression of xt, how can I find it? So ck is the my Fourier series coefficient which corresponds to kth harmonic, and I would like to find it for some particular value of k, and I am also given xt, the function itself, the signal itself, and the fundamental frequency also. So how am I supposed to find ck here, which is the coefficient corresponds to kth harmonic? Let's say someone tell me this is your equation you are supposed to use. So you take xt and multiply with conjugate complex conjugate of your kth harmonic, and that's pretty much it. So let's say what this comes out to be. This is 1 over t. There will be one term. You can see xt contains kth harmonic, which has a exponential, which has is the exact complex conjugate of this. So this will cancel each other. So that would be ck times minus t over 2 to t over 2. Fine. This is one term that corresponds to the kth harmonic in xt. All other terms where I not equal to k will be basically left with I'm writing this here, minus t by 2 to t by 2 c I e to the power j 2 pi I minus k times f t. So let me just take the calculation here. So ck here, according to this formula, I am getting 1 over t ck minus t over 2 to t over 2 dt plus I not equal to k integration ci e to the power j 2 pi f I minus k t dt minus t over 2 to t over 2 this. So as long as this term is only there, I am fine, because this integral would just result into t over 2 minus of minus t over 2, essentially t. So that would be like ck is equal to ck. But what about this term here? This term should go to 0. So as per my calculation, this term here 1 over t minus t over 2 t over 2 ci, it's anyway constants, so let's not care about that, e to the power j 2 pi I minus k ft dt. This thing should go to 0. Can one of you point out that how I can claim that this should go to 0? It's a exponent, like complex sinusoid, right? I mean, if I plan to write e to the power j 2 pi ft, it's same as we all know cos 2 pi ft plus j sin 2 pi ft. Sorry about the c. So essentially this is a complex sinusoid, and by the way here I not equal to k, which we have already seen from here. So this integral is supposed to go to 0 for this expression of ck to hold true. So is something visible to you from this expression, that why it should go to 0 instead of getting into this bit of extensive math? If I would like to infer something from this expression, can I do that? My point is, like, I can still compute that integral here and have the observation that it actually goes to 0. But now with the knowledge we have on complex sinusoid and all that, can we skip that maths part and just infer from this expression only that it should go to 0? Anything you can see that why this term should go to 0? This, let's say this 1 over t is a constant, so let's forget about that. Just a moment. Okay, yeah, 1 over t is constant, let's forget about that. Ci is a constant, let's forget about that. Let's focus on this term. Does this function has any specific property, based on that you can claim that when it's integrated over a interval of t, it should go to 0? Anything you can see here? Okay, let me ask you a question. This expression e to the power j 2 pi I minus k ft, what what do you think? It's a periodic signal or aperiodic signal?
Periodic.
Okay, fine. So, and what is, if I want to talk about its fundamental period is, you mentioned on its periodic signal. Now I want to find the fundamental period. So let's talk about fundamental frequency first, then we can, from there we can get into fundamental period. So fundamental frequency. So what it's going to be? You know, this term here, e to the power j 2 pi fct, this is having a fundamental frequency of f, right? So this term here, what its fundamental frequency going to be? So you can see here, if I compare this expression with this, you see the 2 pi is common, t is common, so let's forget about them. If f is fundamental frequency here, what is the fundamental frequency here?
Into
Nice. So it's I minus k into f. This is your fundamental frequency. And what is my fundamental period?
reciprocally fundamental
1
into
over that, right? Fine. So that is I minus k times f. And what is my 1 over f, by the way?
T.
T, right? So fundamental period is t over I minus k. And I not equal to k, so I minus k is an integer, 1, 2, 3, like that. So essentially this integration reduces to uh, integrating sinusoid over multiples of its fundamental time period. So it's a sinusoid. My integration interval is of duration t, and the sinusoid's fundamental period is t over I minus k, which basically means I'm integrating this one over the multiple times, like let's say I minus k times its integration over its fundamental time period. So what it's going to be, let's try to see from this one here. So if I talk about one full time period, is this, right? I mean, over this entire time interval. So this half positive here, half positive, and this full negative. So whenever I'm integrating a sinusoid over a fundamental time period, what I'm going to get?
0.
0. And if I integrate over multiple of its time period, what's I'm going to get?
0.
0 again, right? So that is what we are getting. So the expression of Ck I have written earlier is turns out to be correct. So by the way, one thing we have learned that for a periodic signal, you have a non-zero spectral component at frequencies 0 plus minus f plus minus 2f, like that. So I would like to extend the same idea only. Instead of seeing Fourier transform as a separate entity altogether, I would like to see that whether whatever we have seen in context of periodic signal and its Fourier series representation, can we extend this for aperiodic signal? I won't like to get any Fourier transform expression, the maths immediately. I'd just like to see whatever we have seen in context of periodic signal and Fourier series representation, can those be extended for aperiodic signal? So just tell me one thing, like what is the main difference between the periodic signal and aperiodic signal?
The values of aperiodic signal doesn't vary after the certain time period. They can vary randomly.
Okay, so can I say, like, let me make this argument, so you tell me whether I'm correct or not. I would like to see a periodic signal as a periodic signal with a fundamental time period t as infinity. So just go through that statement once and tell me what do you think of it. Do you think it's a correct way to write that, or is there any error there? So can I say that a periodic signal is nothing but a periodic signal with time period t as infinite?
Yes, so we may
Okay,
say this.
okay. So
Sure, but
okay, but intuitively you can see there is not like a real fallacy, like something really going wrong, right? I mean, the moment I am
yes,
saying that its fundamental time period t is infinite, that essentially means over any practical duration, that signal is unique and aperiodic. So basically, it's not repeating itself. My claim is that it repeats itself only after like t is infinite. So essentially, it's not repeating itself over any practical time duration. Okay, so now I make this statement, and by making this statement I bring a periodic signal under the framework of periodic signal also. Now everything we have done in context of frequency domain representation of periodic signal, we can do for aperiodic signal also, right? So you can see for periodic signal I have written that there are non-zero spectral component at these frequencies, right? Now I frame a periodic signal as a periodic signal also. Why do you think that non-zero, by the spectral component, whenever I say it, basically it means in the frequency domain, that's all, nothing. So where do you see these non-zero spectral components to appear?
So exactly what's the definition of non-zero spectral components?
Okay, a non-zero spectral component means like this. For example, when we have a periodic signal, just let me, yeah, when we have a periodic signal, we can have this Fourier series representation, right? Whenever I am converting this into frequency domain, that means I have one one frequency domain value at only these particular frequencies, which is the integer multiple of its fundamental frequencies. So these are the one I am calling them at spectral component. That's essentially saying nothing but the Fourier coefficients. So you can just say it's the Fourier coefficients. So that's all. So let me just clarify it. Let's say xt is a sinusoid like this. So this is its time domain representation. Since it's a periodic signal, we can have its Fourier series representation. So that means essentially when I'm bringing xf is nothing but the Fourier like frequency domain representation of xt. Okay, and xf, when I plot it in the frequency domain, we can see that only non-zero values appear at the integer multiples of fundamental frequency, and these values I am calling as the spectral components. You can see xt, when it's in time domain, it is continuous, right? So it has value at every point. But since it's a continuous function, the time domain, it turns out its frequency domain representation is not continuous, it is discrete. So except doesn't have value at any frequency, it has only values at integer multiple of fundamental frequency. So these values I am calling as spectral component. Is that point clear to you, or I would like I need to elaborate more?
Oh, yes, I got an idea.
Okay, okay, sure. So now I am trying to extend whatever we have seen in context of periodic signal to a periodic signal by claiming it's a periodic signal with a fundamental time period t is equal to infinite. So for periodic signal, we have seen that frequency component appears only at this particular frequency 0 plus minus f plus minus 2f. So what do you think is going to happen for a periodic signal also? So first of all, when I say fundamental time period is infinite, what can I say about fundamental frequency here? Let me call this f dash.
Should it be zero?
Yeah, it is 0. So instead of writing it like bluntly like that, let's call it t tends to infinity. So that would allow me to write f dash tends to 0, right? So now where do you think the frequency components will appear for a periodic signal? At what frequencies? It is going to appear at 0 plus minus f dash plus minus 2f dash, right?
Yes.
Now for periodic signal, you had a fundamental time period. That means your t is finite and your f is finite. Both are finite. So that means this gap here between f and 2f, that is also finite, right? But what happens for the
Yes.
aperiodic signal here? Let's say xf is the frequency domain representation of a aperiodic signal xt. What do you think? They are still going to appear as per our understanding at 0 plus minus f dash plus minus 2 f dash. But what do you think the key difference is going to be compared to periodic signal?
The gap between f dash and 2f dash should be infinitesimally small.
Infinitesimally,
It should be almost.
absolutely, yeah, absolutely correct. So if this becomes infinitesimally small, do you think xf is going to have discrete values only, or it's going to change?
It appears continuous.
So it is going to be something continuous. It is still, as per this argument, is going to have discrete things, but since this gap is incrementally small, like kind of overlapping on top of each other, so essentially it becomes continuous. So for aperiodic signal, frequency domain representation is continuous, and that is what we call Fourier transform. So what is the value of xf we get for xt? Xt e to the power minus j 2 pi ft dt. You can still draw the similarity between this expression here. You can see it just these fundamental frequency, there are so many of them, so it's here you can still write them in a discrete manner because the gap is finite, but for aperiodic one you cannot no longer separate them, so essentially you are getting a continuous function of frequency. So this is a nice idea of so let us see what our question was, that for Fourier transform which kind of uh, signal it is applicable to. So Fourier transform we actually find for continuous time aperiodic signal. So let us move to our next question here, which basically talks about if you have a periodic signal, you have a trigonometric series representation. That is essentially just another version of this Fourier series representation. You can see there you have Fourier coefficients, and on top of that you have complex sinusoids that can be separated into cos and sine part. This is being pretty much done here. So it is said that periodic signal xt with fundamental frequency f naught is given as this. So what do you think the coefficient an for n not equal to 0 should be uh, given as? Just a moment. Okay, fine. Yeah, so what do you think we can, how can we find the coefficient an here? Okay, let me help you a bit here. Like let's say when you see that Fourier series representation as follows: k from minus infinity to infinity, ck e to the power j 2 pi ft. There we have seen that sorry, here should be a kft. There we have seen you can find ck as follows. So can you draw a similar analogy here to find what is the coefficient is going to be n for n not equal to 0? Sorry, it's a periodic signal, so it should be my mistake. T over 2. How do you think I can find the coefficient an here? So in the expression of an, we have see that its cos sinusoid is multiplied. So let us try with that. The first one, let's see how xt times cos 2 pi n f naught t dt gets us, and it is become, it's between 1 over 2 f naught and between 1 over 2 f naught here. So if I expand this, what I am going to get, um, a naught integral cos 2 pi n f naught t dt plus an cos square 2 pi n f naught t dt plus I not equal to n and runs up to infinite, ai cos 2 pi n f naught t cos 2 pi I f naught t, and on top of that I will have bn, where I runs from 1 to infinite, sin 2 pi n f naught t cos 2 pi, uh, sorry, here it should be I here, and it should be cos 2 pi n f naught t. Yep. So we can see here what we are going to get. We can immediately see this is a periodic signal with period f naught, and I am integrating over its 1 over 2 f naught. That essentially is same as saying t over 2, right? Minus t over 2 to t over 2, essentially integrating over a full cycle. So this one goes to 0. What about this one? I not equal to n. So this is again going to lead, since I not equal to n, it's going to lead to another uh, sinusoid. And okay, I missed the integration sign here, sorry about that. Should be integration here, dt should be integration dt. So the moment I not equal to n, it is going to result into another sinusoid which has a what is that, uh, fundamental frequency of I minus n. So essentially I am integrating it over multiple time cycle, so that also goes to 0. This one here, sine times cos, lead to true sinusoids, both of them, which will again go to 0 by the same argument, because you are integrating over multiple of its own time cycle, sorry, one time period. So essentially you are only worried about this one here. You will have a cos square 2 pi n f naught term, so that would essentially, let me just do it here, an integration of 1, if I am not wrong, it is cos 4 pi n f naught t over 2, right, dt. So essentially this is another sinusoid with a fundamental frequency 2 f naught. That integration essentially means I am integrating over 2 time cycles, so this part is not of our interest. So essentially we are left with an over 2. Oh sorry, n not n over 2, there is a dt also that runs from minus 1 over 2 f naught to 1 over 2 f naught. So essentially from this particular integral we are left with an over 2 f naught, 2 from here and this one f naught. So essentially this integral I have to multiply with 2 f naught. to get an. So none of the answer looks correct to me. It should be 2f naught here, then it should be correct. So 1 is my answer, but it should be 1 2 is missing. There should be 1 2 here. I'm sorry, I just I was not aware that I was being I'd like to apologize because I was not even aware that I was the meeting has been stopped. So how long has it been? Like I was out. Uh, can one of you please point out like when was the meeting was over? 5 minutes ago or more than that?
5 minutes ago, sir.
Okay. Sorry about that. I was not aware. So have we started discussing this question here or not? So when the meeting was disconnected, have we started discussing this question or not? It would be of really help if you just let me know.
Yes, sir, we have covered some 2 to 3 equations.
Okay. Just let me just repeat it. Let me just erase this thing here. Okay, I need not erase. So essentially, I started with the expression here, the first one. So basically integrating xt times cos 2 pi n f naught t dt. So when I break it down, we are obtaining these four terms. First one corresponding to a naught. So we have a naught integration over cos 2 pi n f naught t dt. So we have seen earlier it is a sinusoid with a frequency f naught, and we are integrating over minus t over 2 to t over 2. So essentially that this is going to 0. Second term, which is of our interest, where actually the n matches, so it would lead to an times one cos is already there, another cos would be provided by the expression of xt. So you'll have cos squared 2 pi n f naught t dt. I'll keep it as it is. The third term corresponds to I not equal to n. So where I get terms of this kind, cos 2 pi n f naught t, cos 2 pi I f naught t, where I is not same as n. So from here I will get two sinusoid which basically have fundamental frequency of I minus n. So that translate to integrating it over multiple of its fundamental time period. So essentially this is also going to 0. The fourth one, similar argument, sine and cos, where essentially that also leads to a sinusoid which has integrated which need to be integrated over multiple of its time cycle. So again this goes to 0. So our term of interest is only this one. So when I do the next step calculation is cos squared theta. So essentially it's 1 plus cos 2 theta over 2 dt. So you can see this is again cos 4 pi n f naught t, that basically have a fundamental period of 2 n f naught. So integrating it over a full time cycle again goes to 0. So what we are left with is an over 2 f naught. Okay, my voice is breaking. Okay. Is it better compared to earlier? I'll just do one thing. I'll just turn off my video, so it is putting a lot of stress on my system, so maybe it would be clear next time. So can you just let me know if you can hear me properly, or the voice is still breaking now?
It's clear.
Okay, okay,
So now audible.
okay, sure, thank you. So I'll just keep my video off so that I see that it's putting more stress and my voice is breaking. So yep. So essentially we are left with this term here, a n over 2 f naught, where 2 is supplied from here and f naught is a integration of dt over minus 1 over 2 f naught to 1 over 2 f naught. So to get a n I have to multiply it with 2 f naught. So essentially the first answer was also not correct because 2 part was missing. So now I put it 2. Now if the answer is 2f, like the option is 2f naught, then only it's correct, otherwise it's not. So 1 is the answer here. Let us move to this the next question, which is kind of interesting from uh, Parseval theorem. So Parseval theorem, what we have already seen, when we have a signal, okay, when we have a signal, we have a time domain representation, time domain representation, and we have its equivalent frequency domain representation. Both are possible. So Parseval theorem, what it does, it creates a bridge between these two. Bridge in what sense? That maybe we have an intuition somewhat now, but it would be clear once we give the answer. So Parseval theorem, you can see, say, kind of connects these two. So what do I mean by that? So for that, let us look at this expression here, which say basically you can already see that this is the Fourier series expression for a time domain signal xt, right? So you have xt, which is k runs from minus infinity to infinity, ck e to the power j2 pi f naught kt. Now even if ck appears in this expression, we already talked about ck are spectral components, so these are more related to, or if we talk about ck specifically, it is the frequency component corresponds to k f naught. So there are two things. One is xt, it's a time domain representation, and then there are the ck's, which are frequency domain representation, or the spectrum we call it. So how these two things connect? So that is our idea. So here we can see at one side it's the power, and other side it's some expression. So let us talk about this expression on the left hand side, where your integration interval is 0 to t naught, and you have to do xt square dt. So it is same as writing 0 to t naught xt times x star t, same only, because x is a complex value, so basically I multiply it with complex conjugate. That's pretty much it. So here I am basically getting 0 to t naught is as same. Here we have k minus infinity to infinity ck e to the power j 2 pi k f naught t, and then I'm using intentionally a separate index here, m cm e to the power j 2 pi m f naught t, conjugate of that dt. So I am getting something of this double integral. K runs from minus infinity to infinity, m also runs from minus infinity to infinity, ck here, c of minus m appears because I am taking conjugate, so this term becomes negative, so when I multiply it's c of minus m here, so e to the power j 2 pi f k minus m, it's not c m minus m, it's c conjugate, sorry about that, I'm taking conjugate here, complex conjugate, 2 pi k minus m f t, uh, yeah, dt. So can one of you please point out how I should uh, compute this cumbersome expression? I have two summation, I have uh, like multiplication. How should I proceed here from here? It's essentially I'm computing the energy of xt over an interval of t, that is this fundamental period, and I'm written xt in terms of its Fourier series expression, and I'm kind of getting stuck here. I have two summations here and this kind of complex sinusoid. So what do you think the next step going to be? Is that true summation going to be there, or we can do something about that? Maybe you can focus on this exponential term here, which has a fundamental frequency of k minus m times f. Do you think it can simplify our case? I mean, if I have to maintain the double summation, it may not be even, I may not have an expression at all. But given that you know that complex sinusoid with the frequency f, when it integrated over or its a fundamental time period goes to 0, can you use some kind of property here that you can see? There is k minus m times f, so that is a essentially a sinusoid with the frequency k minus m times f, and the summation runs over like for both k and m from minus infinity to infinity. So can we do anything about that? Okay, let me ask you what happens when, let's say, k not equal to m. All these cases let us consider. What happens when k not equal to m? I'm looking for this particular situation where k not equal to m.
That exponential term becomes zero.
Okay, so for all, every time k is not equal to m, that should go to 0. Excellent, fine. So then I need not consider all those things. So what do you think I can write now? Would, like, is the double summation still required, or there is some way to get rid of that?
We can write the square of the magnitude of ck.
Okay, since k has to be equal to m to have its effect, basically to have some non-zero values, as you mentioned, I can use a single integral, and as you mentioned, magnitude square, fine, and dt. And what is the resulting expression for this?
Yes, sir.
Okay, so basically this part is constant, so you can take it out comfortably. So it's a dt, so essentially it's t naught times summation of k is minus infinity absolute value of sec square. So the I can put this t naught here as 1 over t naught, and that would make the answer the second one, right? So that is the math part. I'm fine with that. Okay, but I'm still not clear how this kind of connect my time domain and frequency domain representation. Can you help me regarding that by looking at the expression on the left and the right? Like basically what the theorem is saying here.
On one side, it is we are integrating a function, and other side it is summation. So we can say a summation is done for discrete things only, and integration can be done for continuous
Correct,
signals.
correct observation. So can we take this one step further and have some insight regarding the uh, that's excellent, like regarding continuous and discrete, but I was just looking for an argument like where you can really connect the time and frequency domain. I mean the signal remains same, right, in both time and frequency domain. So what is the term left hand domain actually represent? 1 over t naught this whatever is written is the power of that signal in, right, in that I'm domain, if I'm not wrong. Sorry, anyway, by the way, second is not the answer, it's both have t naught, it should be 3. Sorry about that. So on left side we have our expression as you mentioned, where you have xt as continuous, so it's a power expression in the time domain. On the right hand side you mention it's a summation over discrete value, and discrete value is appearing because your xt is periodic, so it has a Fourier series representation whose frequency domain representation only contains non-zero spectral component at the harmonics of fundamental frequency. So that is essentially connecting the power with the spectral components. So it's essentially saying that signal is equivalent in time and frequency domain, in the sense for the same signal you are computing power in the time domain, you can actually observe the same when you take the square of the spectral components and sum it over, so that power remains constant no matter you represent the signal in time domain or frequency domain, so they are equivalent from that perspective. So this is the importance of Parseval theorem, which connects the time domain and frequency domain representation and say that okay, since the underlying signal is same, no matter the domain you use to represent the signal, the underlying power is same, and more importantly you can find them in both continuous and discrete domain. So it is the idea. So this now onwards questions must be quite easy for you, because we have seen that we have a signal with a fundamental frequency of 4 Hz. So what should be the coefficient in the Fourier series corresponding to term e to the power like j 16 pi t? So if I write in terms of 2 pi ft, sorry, 2 pi k, sorry about that, 2 pi k ft, corresponding Fourier coefficient is ck. So ck, another way of saying, is the coefficient corresponds to kth harmonic. So if I am given the frequency 4 here, f as 4, and I am supposed to find the coefficient corresponds to e to the power j 16 pi t, Which harmonic you think we are talking about? My frequency is 4, and my uh, I'm looking for the coefficient corresponds to the sinusoid with the frequency here. What is the frequency content here, by the way? To the power j 16 pi t. If I break it into 2 pi
Second.
ft, yeah, correct. So it's 8. So that means it is 2f. So basically we are looking for C2 here, second harmonic. So C2 we can find it as 1 over t xt e to the power minus j 2 pi into 2ft dt. So what is the t here? 1 over 4 xt e to the power minus j 16 pi t dt.
So one will be 4, right?
Oh, sorry. Yeah, correct. Sorry. It should be 4 here. So which one of the option is correct? Fourth one,
4.
right? Fourth one. So this is another interesting kind of signal which you are going to see again and again in the course going forward. So the Fourier transform in equivalent time and frequency domain representation. So you have this xt is 2 for t less than equal to 10, right? So it's essentially, if I plan to draw it, it's going to be like this. This is my xt. So how do I find its frequency, the frequency domain representation or Fourier transform? This is, anyway you can see, is a continuous aperiodic signal. So I have my xf as so essentially it's running from -5 to 5 to, we can take outside e to the power minus j 2 pi fct dt. Sorry. So it's essentially 2 over e to the power minus j 2 pi ft divided by minus j 2 pi f. So we have e to the power minus j, t is now 5, so essentially it's 10 pi f minus e to the power j 10 pi f ten pi. Sorry. So how can I write? Okay, let us just turn it around. 2 into e to the power j 10 pi f minus e to the power minus j 10 pi f. So this negative term goes there. We have left with j2 pi f. Let's cancel this one. So how I can write this term? E to the power minus e to the power j theta minus e to the power minus j theta.
Then 10 pi f
Okay. Uh, Sine 10 pi f. Any thing I should need to multiply it with?
into 2.
Into 2. It should be 2j, right? If I talk about this term only. E to the power j theta minus e to the power minus j theta over 2j is equal to sine theta. Is that correct, or you want to correct me here?
Yes, yes.
So you have 2j here, and here we have j pi f. So essentially it can be cancelled. We are left with 2 sine 10 pi f by pi f. So essentially it's the third one. Next we talk about Dirac delta function. So it's more or less about property. So can you point out what Dirac delta function really is? Its importance you will see in later going forward in course about how it's really useful in different kind of system analysis. But for now, let's just talk about few basic property of Dirac delta function. So what is the uniqueness about Dirac delta, you think? Okay, so first of all, if I talk about del t, where does it really appear? Is that a continuous function, or it has some fixed value at some fixed point only?
It is a unit impulse function.
Unit impulse function. Nice, nice, good. And what is the height really for this Dirac delta?
Infinite height.
Infinite height.
Infinite.
Okay.
Infinite height.
So if it's infinite height, so and what is its width?
Zero.
Width is zero.
Zeros.
Okay, so basically you are saying that
Zero.
width is infinitesimally small and height is kind of infinite. So when I basically try to take the area under the delta function, comes out to be
Unity.
it comes out to be unity. So of course practically such pulse is not really possible to generate. So we can visualize it like this. So we can in practice we can generate a pulse of sufficiently large height t and sufficiently small uh, width, as you mentioned, 1 over t. Now our only job is like in physical, like when I try to actually generate such a signal, I am limited by my systems like hardwares, where I can only go to a certain extent of t, but in like in pen and paper in theory there is no limitation. So essentially you are saying when I put t towards infinite, I would eventually reach this kind of function. So which one of the property is correct, like one or multiple among these options here?
Third option.
Third one. Okay, so last one is about mt being an aperiodic signal has a Fourier transform mf. So what is going to be the Fourier transform of mt multiplied with cos 2 pi fct? mt cos 2 pi fct. So how can I find it quickly, or and what property more importantly I can use here? So this cos 2 pi fct, can I write it terms of complex sinusoid, that is exponential in any way? Is it possible? I mean, if I would like to compute Fourier transform in traditional way, it's going to take a lot of time and it's inefficient also, right? If I plan to compute, it's like integration of mt cos 2 pi fct over the whole region and then t cos, it's kind of too much. So is there any like shortcut way you can take in based on whatever we have seen in week 1, the content especially? So this cos 2 pi fct, if I plan to write in terms of complex sinusoid like e to the power j something, what it should be?
E raised to j2 pi
Okay, e
3
to the power j 2 pi fct, fine.
plus e raised to minus j2 pi fc upon 2.
Okay, and it's over 2. So essentially this one reduces to this mt e to the power j 2 pi fct plus mt e to the power j 2 pi fc minus here the entire thing is multiplied is 1 over 2. Now this is good. Now how is it going to help me to still find the Fourier transform?
We can use the modulation property.
Okay, I guess by modulation property you are referring to the shifting, right? So this you will see again and again applies for time to frequency and vice versa, that if you shift happens in one domain, that translates to complex sinusoid multiplication in another domain. So essentially what I am trying to see was essentially what I'm trying to say, and you also pointed out. So what you mean by the modulation property, when you shift in the time domain, let's say you have x t minus t naught, so that means in frequency domain you are going to essentially multiply with the sinusoid that is of value to the power j 2 pi uh, 1 over t naught t. And if you have shifting in frequency domain, that would basically leads to complex sinusoid multiplication in the time domain. So that is what you mean by modulation, right? So this property you are going to use again and again so many times, and it's quite a good intuition and time saving. So now what is going to be the Fourier transform of this here? mt to the power j 2 pi fct in terms of the Fourier transform of original m. Yeah, basically I am multiplying with a complex sinusoid, right, in time domain. So what does it translate into in frequency domain? What do you think? Like let's talk from your perspective of modulation. Let's say your mt is your original signal as you were referring to, and e to the power j 2 pi fct, which is basically sinusoid with the carrier frequency of fct. So when you say modulation, what do you mean? What will happen to the original signal?
F minus F the frequency.
Okay, so it will become mf minus fc. That means it would basically shift in the frequency domain, right? That is very fundamental idea of modulation, which you will see in the next week onwards. That you have a message signal at some lower frequency. Now you will see that when you want to transmit the signal, you cannot transmit over a low. Uh, you have to transmit over a carrier frequency to avoid like multiple things. And the way to do that, you multiply the complex sinusoid in time domains. Essentially, that would shift the spectrum of your message to a higher frequency. That is the key idea in communication. So this is m of f minus fc. What about the second one? What you will get there? So you mentioned this will have Fourier transform shifted to fc in the right side or in the positive side shifting. What happens to this here?
F that's
F plus fc here. So you just make use of the time shifting property and you would immediately get the what the Fourier transform is going to be, avoiding all these maths. So here, yeah, the first one. So this is pretty much all I have to discuss in today's session. So if you have any questions regarding today's content or anything in general about the course, you can ask me now, or you can also contact me over email if you have any queries. I tried my best to solve them. And if you don't have any question, we can end this session and we'll meet next Saturday. The slides and video will be both uploaded. I think you already have seen in the course there is this that problem solving session title part where you can access the video recording along with this PDF also. So any doubts, anything?
Sir, does this session happens every Saturday?
Yes, every Saturday 6 to 8. If maybe there is some emergency from my side, it may change, but most likely it's going to be 6 to 8 you, every Saturday.
Okay, sir.
Sure. So if there is no more questions, I would end the session. So before ending, anything you'd like to ask? I mean, if you are not comfortable now, you can ask me later. I have provided the email also. You can find in the PDF. Okay, thank you all for attending this presentation the entire time. I really enjoyed it. If you don't have any questions, let's meet next Saturday. Thank you, thank you, thank you. So,
Thank you, sir. Thank you for your valuable time.
sure, sure. Thank you. Okay, good night, everyone. I'm ending this session.